Should we already? Okay. Three, two, one. Okay. Hello, guys. My name is Kirtana.
I'm Lakshya.
I'm Shibhi.
We Team 25 presenting ranking aware unbiased post click conversion rate estimation via AUC optimization on entire exposure space. Here is the overview of our presentation, which consists of introduction, problem, related work, proposed solution, implementation, and results. We are going to explain everything in detail.
Starting with the main objective of this paper. The main objective of this paper is CVR estimation. So, what is CVR? Before considering that, let's consider an example. Suppose we went, suppose we go to an online website and then we see some ads. We might find those ads like appealing and might not. If we find those ads appealing, we might click on them. If we click on them, we might be redirected to some other website or some other web page in which there might be some product advertisement and maybe we buy from there. If we buy a product after clicking through an ad is called conversion. So basically every instance have three components: exposure, click and conversion. Going to the main website and viewing these ads is called exposure. Clicking on an ad is called click. But after clicking, maybe buying a product from there or maybe agreeing to whatever that ad says is called conversion. For example, if a user wants to buy pants and shoes and goes to a shopping website, the user can see multiple ads regarding all kind of clothing like tops, t-shirts, skirts, dresses, shoes and pants. The space consisting of all these items is called the exposure space. Now, the user might like the ads of a t-shirt and a pants as shown in the diagram and might click on them. So the click space is the items which consist of the pant and the t-shirt that the user clicked. This is denoted by O and the items which he did not click on is called O bar. Now since the user was only interested in buying pants, he bought the pants. So buying this pants is called conversion. This is denoted by CO. That is the intersection of the C and the O part in the previous two diagrams. So basically we get to know two new terms, CVR and CTR. CTR shows the measure of how often people click on an ad when they are exposed to it. CVR shows the probability of a transition from a click to a conversion. Why do we want to know this? We want to know about this to understand users' behavior, to how frequently do they click on the ad, to how frequently are they going to buy from an ad, to get to know if the ad is productive or not. So we want to do CVR estimation, but while training our model, we face two main problems: data sparsity and selection bias. Let's delve into them deeper.
So the data sparsity, like a user might be seeing many ads, but like he might be interested in some products. So he might not be actually clicking all those ads. He might be interested in only some of them. So even right before the CTR stage, we are not having much data. And then even though the user might be clicking on an ad, he might not actually be buying or doing whatever the ad is saying. So the actual data for CVR is even getting lesser. So like this gives rise to the data sparsity. And then one more problem is the selection bias. As the name itself indicates, is the bias in the selection. Like the user might actually want to buy something, but the ad might not be appealing. Even though the user want to buy it, it might not end up buying it. So like from this thing, we can imply that having a higher CTR might not always imply having high CVR, and then having lower CTR might not always imply having lower CVR. So what we want, like we want to build a model which is an unbiased estimator. Like it should not show any selection bias, and also it should like cover all the entire exposure space. Like all the items should be covered.
To deal with these two challenges, previously many researchers have worked and created some models. Their work can be classified into two broad categories. One is dealing with the data sparsity, second is dealing with the selection bias. So mainly the models that are dealing with data sparsity consist that consist a relation between CVR and CTR. As we have seen earlier, we can say that CVR is a post step of CTR. Once the user click on a particular ad, he can decide he wants to buy or not. So basically, the models here leverage multitask learning because CVR and CTR both share the same input features, that is the exposure space. One example of this kind of model is ESMM model. But there is a drawback in this kind of model. The drawback is that we sacrifice the unbiased CVR estimation, and there is a lot of loss of information that we might have gotten through non-click events. So now we discuss about the other type of model that deal with the selection bias. In this model, what happens is to remove the selection bias, the input features only consist of data which which are already considered in CTR. That means the users have already clicked on it. So here there is no bias problem, but the problem is we are not considering the overall dataset, that is the overall exposed space. So this model can only estimate CVR within the click space. Some example of this model is multi-IPV and multi-DR model. So basically there is a trade-off between unbiased estimation and covering of the entire exposure space. To deal with these problems, let's see how the researchers in this paper have worked through it.
So before going to the architecture of the model, let's focus on the loss function. The loss function preferred in this paper is AUC, area under the curve. So first of all, what is AUC? Like in general classification problems, like there can like the classes can be divided into two things: the positive instance and the negative instance. Like AUC gives the probability of the positive instances getting higher rank than the negative instances. So what are the positive and negative instances in our case? Actually, there are three instances in our case, which are positive instance, zero instance, and negative instance. Positive instance correspond to the user clicking on the ad and also buying the item. And then the negative instance is the user clicking on the ad but not buying the item. And then the third case, the zero instance is the user not at all clicking on the item. AUC gives the probability of the ranking. And then what's the maths behind the AUC? Like AUC is actually the area under the curve plotted between the TPR, true positive rate, and FPR, false positive rate. So how does AUC help? Like as we can see, like like AUC helps in four issues. Like first is like we can consider the usual evaluation metrics, which are accuracy, precision, recall, etc. But they only focus on like yes or no classification. Like if we use those in our case, it will end up saying whether the user will go in that ad or not. But that is not actually our problem. We need to rank all the items that user might visit. So like in our case, ranking is better than classification. So AUC helps us focus on ranking rather than the classification. And the second one is, as we have already discussed, there is selection bias in our data. And then like the user might end up click on an ad or not might not click on an ad. Like there's some discrimination to so AUC like choosing ranking over the classification helps to reduce this. Also, like even if the user clicks on the ad, he might not actually end up buying that. Like most of the times, he might not actually end up buying the item. So, like there is this data imbalancement. There is this data imbalancement. So ranking helps to decrease the imbalance in the data. Also, like we sometimes we might not actually have the label data, so we can't really use classification on unlabeled data. So using ranking, we don't really need the labeled data. So we can even get more data, that is the unlabeled data, and we can use it for our model.
These are our proposed solutions, which consist of three parts. The first part is unbiased AUC optimization based on sample weighting. Here, what we are doing, giving weights to all the samples through by minimizing AUC risk, click through, even probability distribution. Here, the bias problem is actually solving, but the data sparsity problem will still exist. And the second part is unbiased AUC optimization on the entire exposure space. Here, this will be discussed in the further slides in more detail. And the third one is multitask learning module, which is an approach to estimate the CTR and CVR jointly. Unbiased AUC optimization based on sample rating. Because of selection bias, we do not have info about data a user did not click. Therefore, ranking of data would have been higher, which might not be true in reality. To reduce this effect of selection bias, we assign some weight to all data points. Then we try to minimize the risk using the click-through event probability distribution. Here our risk function tries to give higher rank to positive instance than negative instance. The positive instance is the one where the user is clicking and the conversion is also happening, and the negative instance is the one where the user is clicking but the conversion is not happening.
So coming to the second layer, it is the unbiased AUC optimization on the entire exposure space. Like we are using the term entire exposure space here because in the previous layer where we only mitigated the bias, we consider the positive and negative instance, but the zero instance where the user is not clicking on the ad is not considered. So in this layer, we are going to include the zero instance too. So how are we including this? So, the loss function in this layer, it can be divided into two parts. The first part is comparing the positive and is the loss function between the positive instance and zero instance, and the second half is the zero instance and negative instance. So we'll choose a hyperparameter beta, and then we will make a linear combination of the risk, which is explained in the previous layer, and then we will make the linear combination of the risk between the positive and zero of the first part, and then the zero instance and negative instance for the second part. The resultant risk helps us mitigate the data sparsity too because we are including the zero instance. Selectivity bias is already mitigated, and then this helps us decreasing the data sparsity. But does this solve all the problems? No, because we are considering the zero instance, but we don't actually know the distribution of it. That is, we actually don't know the actual CTR distribution. So how can we find it?
Since we do not have access to the real distribution, we try to find an approximation for the distribution of CTRs for any event X. We do this by utilizing multitask learning for both CTR and CVR. So why can we do multitask learning in this problem? Since the input space for both CTR and CVR is the same, which is the input features and the input user features and the item features, they both share the same input space. So basically what we do is we use the same parameters that we use for CTR in CVR. So this reduces the time and space complexity and reduces the time required for training as well as the space required for training. So basically in the earlier part what we did was we trained for both the risks separately. But here in this part what it does is it considers CVR and CTR to be same model but different tasks in the same model. So basically what happens is it leads to a substantial reduction in the training time. But how does it actually do this learning? Let's see in the next slide. So as you can see in the exposure space, that is the input features, we have three type of data that we have already discussed: the positive instances, that is click through and conversion event; the negative instances, click through and non-conversion event; and the zero instances, that is the non-click through event. They share the same feature space. So what we do is we do the embedding together, and then we have two tasks, that is to find the CTR and CVR. We train them as like for CTR we use the EWAC laws that we discussed earlier, WAUC laws that we discussed earlier, and for the CVR we use EWAUC, and then we find the losses for both these trainings, and we find the combined loss, and then we do back propagation to reduce the overall loss. So as you can see that we are not doing backpropagation separately for both these tasks. but we are doing it together. Therefore, it is reducing the total number of parameters and the training time. And that's how the model training is done. Let's move on to the results.
Here is our results of our models. The first few models are the ones which solves the issue of selection biased only, and the last few models are the ones which is solving the data sparsity problem only. But the final one, EWAUC model, which is solving both the selection biased and the data sparsity problems, which is, as we can see, that model is giving in better results compared to the previous models. So, yes, thank you.
This is Team 25.